All right, this is the first demonstration of 3 of the weaknesses in assignment 2 to causal and concurrent messaging. So in this, there's a delay of 5 seconds between messages going from Alice to Charlie. So in this time, if Alice message, Bob the messages will be received out of order by Charlie. Alright, this is the second situation, which we discussed in response to the idea of global timestamps. And this, 2 things happen concurrently. Alice broadcasts a message to everyone, and Bob broadcasts a message, and Charlie, in response to Bob's message, broadcasts another message. However, Bob's message is delayed en route to Daphne, meaning that, message, meanwhile, is... Daphne sees Charlie's message before Bob's message, and so the causality is lost, and this would not be solved by global timestamps because Daphne would would see a different global timestamp for Alice's message, because it would be the first message, and Charlie's would be the second, and it would not detect anything until Bob's message arrives, however long that takes. For the third situation, we proposed a system where messages are sent with a timestamp of the immediate preceding message that caused it. However, we realized that doesn't account for situations where a message depends on multiple messages. So, for example, Alice and Bob both broadcast messages, and Charlie broadcasts a message that's a response to both of them. And so, message were to be sent with only information about the immediate preceding message, then clients that receive these messages wouldn't know that Charlie's message depends on Alice's message. And as we see in Daphne, our fourth person's record, Alice's message, which doesn't arrive until after Charlie's message, is not recognized as a causality error. So I implemented the vector timestamp protocol that we outlined in class with a couple of changes that are the same as the changes that I outlined in the exam. Mainly that the vector timestamps are only updated when a message is received, and each user sends a message to itself in addition, which really shouldn't cause any problems unless a user somehow manages to send multiple messages before it's able to receive any of those messages at once, in which case it'll flag as concurrency, but that's perfectly fine because this also includes concurrency recovery. So I also built in data structures, one representing a matrix of the delay times between users. So that could be set on startup, and so we can simulate any sort of situation. And the other data structure is automates the sending of messages. And so I no longer have to use quick finger work in order to simulate each of those scenarios that we outlined, because they can now be automated. And so, for example, the automation will begin as soon as any message is sent. So in this case, this is the first situation where Charlie was receiving the messages out of order. And so since Charlie didn't send any messages in that, we'll have Charlie send a message, start it off. That's not going to interfere with any of Alice and Bob's timestamp. And we watch Alice and Bob immediately broadcast their messages. Charlie has actually already received Bob's message, but waits to receive Alice because it recognizes from the timestamp that there's a preceding message. And now all 3 users have the same view of these messages. So there was one bug that I came across, some peculiarity, where the last user to join the system, messages sent by that user would be received with the username null, and that user would not be able to receive any messages. I'm really not sure why that was happening. It only happened when the filters were inserted. I think it might be a bug in group messaging. I'm curious to see if anyone else had that issue, and what might have caused it. No, I do not want to change the color scheme of Windows 7. So the solution that I had was just for these scenarios where we had 4 users, I just created a 5th user, Eustace, so we have an E. And so what's really odd is that it's only the last user. So like when I created started running Daphne wasn't working right. But then you create Eustace and Daphne suddenly starts working, which is really weird. Anyway, this is the second scenario, and so we have Eustace hanging out here, but we're not going to use him. This is the second scenario where created a response to the global IDs, where Alice sends a message to Daphne, and Bob and Charlie. Charlie sends a message in response to a message received by Bob. And so what we're hoping to see is that, one, concurrency should be detected. These since there are 2 things happening concurrent, each client should recognize there's concurrency, and that flag button says concurrency has not been detected. It's going to change to say concurrency has been detected. And the other thing we should observe is that Bob's message should not be displayed before Charlie's message. Any client. And after the delays on Bob and Charlie get through, there we go. We see that for each user, Bob's message arrives before Charlie's. We notice that these users do not have an identical view of the chat history because of the concurrency. We do not guarantee that each user gets the same view, but we do guarantee that causality will be respected. And here we notice that concurrency has been detected by each client. All right, and this is the third scenario, again, where Charlie's message depends on 2 other messages, one from Alice, one from Bob. And so what we're looking for when this runs is that Charlie's message should not be displayed before Bob's or Alice's on any... And no, stop asking me. I don't want to change the color scheme to improve performance. And we're going to see that not every view has the same ordering of messages because of concurrency. Alice and Bob, from their perspective, both broadcast their message first, so we see it in a different order. But for all 4 of them, Charlie's message is last, and all 4 of them have detected the concurrency. So causality detection can be turned on and off at a client. When it's turned off, that client any messages immediately. And when causality is enabled, it resets the timestamp at that client, which probably will cause some other issues if clients are anticipating a higher timestamp from that client. They say, like, oh, I've already received 3 messages from the client, and the other client's like, I haven't sent any. But it really, I don't know how much sense it makes to be able to enable and disable causality control at specific clients, but that's just part of the specification of the assignment. Disabling causality is simple. Empty buffer. It's not actually doing that. The messages get lost. I followed through, I stepped through everything, and the messages were being removed from the buffer and being sent to the processor, and I even stepped through the processor, and they were sent to the dispatcher, and then the messages would kind of vanish. I don't know, but I hand them off to the group messaging code, and they just never arrive. The view never gets alerted to the communicator never receives it, which is really weird. So this is the code for the buffer of sent messages in package nakobi.dcs.lab5.concurrency class sent message buffer. I can't demonstrate it because of that aforementioned issue where when a user joins the session, they can't receive messages. It's very odd. It turns out I did a little bit more digging. Even though this is added as a session message listener to the communicator, the client joined is never called, which is really odd, and I haven't figured out why that's happening. But you can look at this code yourself. It's pretty simple. Essentially, when a client is joined, it buffers every message that's sent from this client. When another client joins, it just sends them all to the client. And if the other client has causality control enabled, then it will be able to order all the messages. One last note about event tracing. Probably at several times during this video, the console was visible showing events as they were popping up. There was the user added to vector timestamp event does not fire in this. I chose not to use that event trace because the timestamps are represented internally in this application as a map of string usernames to integer values. And so not only does it not really make sense to add a user to the timestamp, because the behavior is if a name isn't in the map, its value is considered to be 0. And so the string isn't actually put into the map until the time when it's first incremented to 1. So it doesn't make sense. Nothing happens when the user joins, and it doesn't really make sense to have a user added to vector timestamp. There also wasn't really any good place in the code for it, because the only part of the code that could be able to detect users joining was the send buffer, and the send buffer doesn't have access to the client's timestamp, and I wasn't going to expose that just for that event.